Okay, the second chapter of the surface engineering methods, which are used to fabricate coatings, is those referred as the set of thin films technologies. Why thin with respect to thick, which is the area of the thermal spray methods? Because in this case, the mechanism of fabrication of coatings is completely different from those we have seen in the area of thermal spraying, and thus also due to very low deposition rates which characterize this set of techniques under the thin film technologies, we do have, on an average, maximum coating thickness, which is around some micrometers. We can go very down in the thickness up to 100 of nanometers, even though they exist, but they are special cases, like those, for example, for fabrication of ceramic fibers used in composite materials. Even though they exist, let me say again, as exception, thickness of coatings which can reach 100 and 150 microns. But on an average, for the techniques which are not used for fiber fabrications, but for coating fabrications to our purposes, we have the upper limit, which is around some micrometers. Some means 3, 4, 5, 6, sometimes 10, but no more. So the goals of the set of techniques, there are many, for which are named thin film technologies, could be essentially looking to the real applications existing on the market, divided into two lines. The first one is related to electrical or optical devices, which are small and cheap. The second one is related to the fabrication of coatings, that is to make materials in textiles, for example, in engine blocks, for example, for tools, for example, for some special cases of barrier coatings, having, let me say, the role to give to the surface a higher durability. And in this case, for example, we are talking about protective coatings, or make the same surface more stable with respect to the interaction that can be established with the working environment, like, for example, conferring to the surface a higher oxidation resistance. For what it concerns our interest, I mean the interest in this course, we will talk essentially about the techniques which are used to fabricate coatings, not for electrical or for optical devices, but generally saying to give to the surface a wear resistance or a corrosion resistance which is higher than the untreated surface. In order to make some initial summary on this topic, we can say that when we are dealing with thin film technologies, it is also possible to make a choice to fabricate, for example, multi-layer coatings. That is, to use thin layers, one on the top of the other, having thicknesses, each one very, very small, and in any case, reaching, for example, the final coating thickness, which can be a composite coating, as an example, again in the range of thickness that I have specified before. And so thicknesses, as you see here, of the single layer can range from something which is around 10 nanometers, 100 nanometers, to several micrometers. That depends on the final coated thickness which is desired. Examples of applications, for example, they are made by these kind of techniques, anti-reflection coatings on glasses, or anti-oxidation layers on metals or metallic alloys, or in some special cases, ceramic coatings to prevent overheating of the component, or functional coatings. This for glasses is quite usual, to confer to the surface an hydrophobic properties, as well as I have said before, wear-resistant coatings. One very common, let me say, application, which is outside our field, are anti-scratch coatings, which are made, for example, on glasses of mobile phones, just to give to you another examples. In order to establish the fundamental of these classes of processes, with respect to what is going to happen in comparison with thermal spray technologies, in thin film deposition, due to the fact that the final coated thickness is very small if compared with the thermal spray processes, we need a very clean substrate and as much as possible a flat surface. In order to, that means very low roughness values of the materials, which represent the base materials onto which the film will be deposited. So first of all, we need, in any case, something to coat. That's again a substrate, the base materials. Then we need a source, which is able, we will be more precise on this film, on this area, which is able to give to us the materials which is selected in order to fabricate the coatings. We need together with this source of film materials, also some process which is able to bring the source materials in contact with the substrate and let it stick on the substrate, that is, have a good adhesion between the coatings and the substrate to be coated. And then in some cases, that depends on the application, it could be also necessary to have in the steps of fabrication technology patterns and etch the film in the case we need very special geometrical final configuration of the surface. Which are the most important deposition technologies, which are important deposition methods? We have two areas. I have selected for you two areas, which are the most important for let me say, for us. The first is a solution processing based coatings, which is the so-called spin coating technology. And the second area is the area of the vapor-based deposition technologies, in which we do have the chemical vapor deposition processes and the physical vapor deposition processes. I say processes, not process, because we do have the general outline of the process, but the number of processes which are under the head of chemical vapor deposition are very relevant, as well as the number of processes which belong to the physical vapor deposition processes. And if we make a comparison for our purpose of the importance between solution and vapor deposition processes, the last one, that is the vapor-based, are the most important and onto which we will put mainly our attention. What is solution processing anyway? Solution processes, the terms defines the technology. We start from a solution which is made essentially by using conjugated polymers and soluble materials. And so we do have this film material, which is dispersed, which is dissolved in a solvent. A drop, for example, of these materials dissolved in a solvent is placed on the substrate to be coated, and then by rotation we can use a spin coater or a doctor blade to spread the film on the surface, let the solvent evaporate, and thus remaining on the treated surfaces by substantially a chemical approach, if we want to say, solution approach, a chemical approach, the final coating fabricated. If we move to the most interesting for us technology, chemical vapor deposition is the fourth class. It is also called CVD as acronym. Is an ensemble of technologies which are based on the existence of a chemical reaction essentially between, because most of times there are two vapor sources, two gases, essentially two gases. They represent the materials precursors. This chemical reaction will happen on the substrate, that is on the materials to be coated, on the component to be coated. And most of time, with the exception of some special cases like those represented on this slide, the chemical reaction gives rise to a product of the reaction, which is a solid together with a gas. So we start from a vapor phase, a gas phase as reactant, materials precursors. Then it happens the chemical reaction on the substrate. One of the product is a solid. This solid is the coating which is deposited onto the surface. Instead, when it exists, the residual gas phase must be evacuated. In some cases, like those reported here in the semiconductor industry, we do not have a chemical reaction, classical chemical reactions, but we have a chemical reaction which is a decomposition. And this one reported here is, for example, as you can see, the decomposition reaction, which is used in CVD technologies to fabricate silicon-based surfaces. You see also we do have, in this case, a residual, which is a gas phase. It is hydrogen, which must be evacuated from the area in which we are going to perform our process. Most of times, I would say 100, but some examples not falling into this category, they are still existing. So let me say most of times, the reactants that we use, they are harmful for the environment, for the operator, that is for the people. So these chemical reactions must be confined into a chamber in order to control all safety issues. And into the chamber, the part which must be coated is loaded, the process is performed, and the coating fabrication happens. If we move instead, just as a general definition, to the second class of vapor-based technology, the so-called PVD techniques, that stands for physical vapor deposition. In this case, we do not have chemical reaction to fabricate the coatings, but we use, and this is the reasons of the name, physical means, which could be, as we will see, heating, ablation, or plasma, to generate from usually, not exclusively, a solid source, a vapor of the material which must be deposited in the forms of thin film. And what it happens that, for example, the atoms or molecules, that depends on the material's composition of the materials with which we want to fabricate the coatings, after the generation of the vapor by physical means, they must travel, or they are guided onto the substrate. In that case, they condense, and so we get the deposit and we get the fabricated solid coatings. Since we do have here the necessity to generate a vapor phase, starting from, for example, from solid materials, which represent the materials with which we want to fabricate the coatings, we need energy to be used in order to let the vaporization steps happen. And usually, in order to have a suitable value of partial pressure of the elements or atoms or molecules which will then deposit to form the coatings, this class of processes must be and generally requires vacuum. That means that also in this case, we do have a confined chamber in which we load the components to be coated, in which we let happen the physical processes to have evaporation and then condensation and then coatings. But if this chamber in the CVD technologies is essentially related to the use of dangerous precursors, in this second case, it is most important, generally speaking, because we do have to allow a vaporization process from a solid source. And so, in this case, the reasons of the use of a chamber, of a defined space in which the process is performed is directly linked to the physical means that we use to get vaporization of the solid, which represent, if we want to use the same terminology, let me say, the precursor material with which coatings will be then fabricated. Let's go on. Here you have the most, they are not all, because there are much more, but the most important, let me say, deposition techniques, which falls under the umbrella of PVD and CVD processes. For the physical vapor deposition, we can have an initial distinction about the way in which the vapor phase is generated. And so we can have the vapor phase generated by a direct evaporation. And in this case, we do have the processes which are based on thermal evaporation or on electron beam evaporation. Or we can have also, and they are quite used, generation of atoms or molecules in the vapor phase, that is the materials with which coating will be fabricated by sputtering. And in this case, we can have direct current sputtering, or magnetic sputtering, or radio frequency sputtering. And as we will see later on, this is a technique also useful to establish a variant of the basic PVD process, which is called reactive physical vapor deposition. What does it mean? It means that atoms are put in the gas phase by sputtering, for example. Then they can meet an atmosphere with a special composition. Think again, just to have a reference, titanium and nitrogen. This atmosphere can react with the atoms in the gas phase and forms, for example, titanium nitride. And in this case, we will have the fabrication of titanium nitride coatings, which has a composition different from the initial bulk materials from which we have generated the atoms or molecules which will then deposited. For what it concerns instead, the chemical vapor deposition, for which, as we said, the coatings, the film, is formed by chemical reaction on the surface of the substrate, we can have the low pressure chemical vapor deposition, we can have the class of plasma enhanced chemical vapor deposition, or atmosphere pressure chemical vapor deposition, even though also in this case, they are processes in a confined chamber. They can be performed at atmospheric pressure. Or we have another special case, which is essentially for electronics devices, which is called MOCVD, that is metal organic CVD, due to the fact that the coatings will be made by materials belonging to the class of metal organic materials. For the general characteristics of thin film deposition, as we will see also later, we do have very low deposition rates, very low deposition rates in an optimized process. I have in mind, let me say, what is going to be used, for example, in a standard way for wear resistance coatings in order to achieve, for example, 5 microns of coating thickness. We could need a processing time which is of the order of 5 to 10 hours. So that means that the deposition rates is very low if compared with the thermal spraying processes. Then we do have the parameters which must be controlled, which refers to the film uniformity, both across surface uniformity and run-to-run uniformity. If, for example, we are going to fabricate multi-layered coatings, the materials which can be deposited in general, they can be metallic materials, these metallic alloys, but also dielectric materials as well as polymer materials. And the quality of film is evaluated by physical and chemical properties of the film itself. And so we do have, as we have seen, techniques which are able at lab scale to allow us to make our characterization testing in order to evaluate residual stress where present, the adhesion, the stoichiometry, that is the composition of the film density, and eventually the defects density, the grain size, the orientation of the grains. For dielectric materials, the so-called breakdown voltage, and the general also in terms of composition that is related also to stoichiometry of the film itself, the presence of impurity level. The deposition directionality can be directional or non-directional. And the techniques, these kind of techniques, they do require, let me say, equipment which are not quite cheap. They are quite expensive, but the benefits which can be obtained by looking to the life of the components so treated can justify, in terms of cost to benefit ratio, the choice to modify the surface by using vapor-based technologies. Again, this is something which add cost to our fabricated components, and thus it is used not in general, like, for example, the thermal barrier coatings, but it is used only where it is necessary, because the components will be more costly than components not treated. PVD. So the black box, or the box with which we can make a sort of scheme of the PVD, starts from the presence of the materials which must be evaporated. Generally, it can be a solid or a liquid, but most of time it's solid. And this is the condensate phase. You see here, it is used quite confusing terminology, but this is the international, let me say, standard. So it is important just to know it, because this one, the condensate phase, is called target, but it is called target because on that they are activated mechanism in different ways with which we will obtain the evaporation of the condensate phase. So we have the generation of a gas phase, which must be transported, this gas phase, where on our substrate on which we want to fabricate the coatings and on which we do have the condensation of the evaporated phase, and thus the coatings is then fabricated. We have seen before, just come back one moment here, that if we are talking about the PVD techniques which are based directly onto evaporation, like in this scheme, we do have two different classes. The first one, if we are, let me tell it better. If we are looking to the way on which this vapor phase is formed, we can have a direct evaporation, that's the first class, and sputtering, that is the second class. And what does it mean? That in the direct evaporation, we have our target, which is here, solid or liquid, mainly solid, as I said to you, inside a chamber where we put vacuum, very high vacuum with respect to the 50 millibar, which are instead requested, for example, in the vacuum plasma spray processes. This means that all the system of the pumping unit for the PVD, and it's another, let me say, reason of cost, is more performing than those which is used in plasma or thermal spray based technology. And one possibility for the thermal evaporation is, for example, to put heat on our target. So we have called it target, that is the source materials. And due to the presence of vacuum in the chamber, the vapor pressure, that is the evaporation of this solid phase, generate the gas, which will be then deposited by condensation on the substrate. This system, that is the system, the standard, the most simple, if you want, system to get evaporation by thermal effects, is the less expensive, but it has a limitation, because obviously it is possible, in order to achieve suitable deposition rates and a suitable performance of the processes, only on low melting point materials used for coatings, like, for example, optical fins. Then we do have nothing inside, just evaporation and condensation, and so generally we have also a weak adhesion of the coating on the substrate, but it can be useful for some kind of applications. Sometimes, in order to strengthen the adhesion, to reinforce the adhesion between the coating and the substrate, some, let me say, post-thermal treatment, that is a reheating to let interdiffusion happen, is made at industrial level. The second class is sputtering, as we said. In this case, sputtering is made by the use, we will see later on better the scheme, of ions, which are generated inside the chamber, for example, argon ions. These argon ions, they impinge on the solid, and then they sputter out atoms from the surface. And so in this case, then we will have the atoms previously on the solids, which are sputtered out by the energy transfer due to the impingement of argon ions on the surface, and this represent, let me say, the atoms which then will be condensed on the substrate. And so we do not have here with the sputtering a classical evaporation, a classical transition from the solid state, that is sublimation, to the vapor state, but we do have amine ions which by impact on the surface transfer energy and let atoms to go out in order to have the gas atmosphere from which then we will activate the condensation process. You see here, if we put inside, as I was telling to you before, inside this chamber, a reactive atmosphere, for example, nitrogen, and for example, having as a substrate, just to give you this, always the same example, which is most common, titanium, we can have reaction inside this chamber between the titanium atoms and nitrogen, and we can have the formation, for example, by chemical reaction of titanium nitride in the vapor phase with a condensation on the surface of the substrate and the fabrication of titanium nitride coatings. This is what is called reactive physical vapor deposition techniques. It can be made with nitrides, can be made with carbides, can be made with oxides if we put here the suitable atmosphere in order to let the atoms sputter to react and having thus a different composition from the starting materials. Evaporation. The evaporation, as I told to you, is the most simple way to have, that is sublimation, a gas phase in order to allow the condensing phase of the PVD. Let me say, in this case, again, the most simple configuration is that we get evaporation and suitable evaporation by heating our target, that is, by heating our source. And how it can be done. For example, the load source materials, that is the target, can be put inside a crucible. And this crucible can be heated by letting current intensity to flow around the crucible itself. And so by Joule effect, we do have heating of the solid phase, which is inside the crucible, and we have the evaporation phenomena. And this evaporation phenomena is able to establish an atmosphere which is rich of the elements which have been evaporated. And if you put in front, for example, of the crucible, the substrate, you can allow the condensation process and the fabrication of the film. So the evaporant condenses on the surface and it's absorbed by the surface. So it's a very simple mechanism. If we want to discuss the principles, even because very simply we can have, here you have some examples, we can have heating by current by using a resistive wire, that is, as I said to you, by relying on the Joule effect. But due to this simplicity, we do have some limitation. One limitation is that in order to have a suitable value of partial pressure of the materials coming out from the source by sublimation, we need to use generally with this simple configuration low melting point source materials. We can have also some contemporary effects of evaporation of the materials with which the crucible has been fabricated. And this can represent, let me say, a drawback, because we will have contaminants in the deposited film. And so this again goes into the direction to, let me say, not stress too much the materials of the crucible, that is putting inside the crucible itself a low melting point materials in order to limit the maximum allowable temperature, and thus limits also the number of the percent, the concentration of contaminants coming from the crucibles, which can represent undesired effects on the coating final composition. This process of evaporation can be quite easily, let me say, studied by remembering that for each element, for example, we do have the possibility, depending on the temperature, and so we have diagrams which are helpful for us, which give to us which is the vapor pressure in bar or in another unit on the solid surface. That you see, if you increase the temperature, the vapor pressure is going to increase. So generally speaking, even though the rates are very low, we can expect an increase of the deposition rate. But being, if you see here the unit of measurements, so low, the vapor pressure, so in order to have an atmosphere for which we can then establish a concentration of the evaporated phase from which the coatings will be fabricated, which is sufficient, we need to work, as we told before, in vacuum. We can have a variant of the standard evaporation system by thermal heating, by using the so-called electron beam heating. So it's the second option that we do have in the evaporation-based class of the PVD processes, that is not sputtering. In this case, what is done? It is generated by a cathode filament, as it happens, for example, inside a scanning electron microscope. It is generated an electron beam, that is a beam of electrons. This beam of electrons, being electrical charges, can be guided, that is, can be focused on a point and positioned on a point by using a magnetic field. And by, let me say, the energy transfer due to the fact that the electrons are focused on the solid materials, which represents again our source or our target, the resulting heat transfer is the energy drive force in order to have evaporation. That means evaporation by electron beam, not using heat, not using resistance, not using the Joule effect, but just using the dissipation of energy, which are related to the fact that an electron beam is focused and pointed on the surface of the target materials, which is the advantage of this method with respect to the other one, is that since we focus our beam directly on the source materials, essentially we can expect, and this is the case, a very low container contamination on the finally fabricated coating. Let's have a comparison between these two possibilities, basic possibilities, that is the thermal evaporation and the electron beam evaporation. You see the thermal, as we said before, it is used essentially for metal or low melting point materials. Here you have a list. we do have, and we can expect a high impurity level inside the coating itself. They work and they require temperature range which is at minimum around 1800 Celsius, and the cost, if compared, of the equipment with respect to the electron beam is low, since the principles are just in comparison are quite simple. In the electron beam, we can use as starting materials metallic materials, but also dielectrics materials. And here you have some added materials with respect to the previous classes. You see, we have also ceramic materials which can be deposited. Due to the fact that the crucible is just a container, but the thermal energy by the electron beam impact is transferred and is focused on the target materials, we have a low impurity level in the coatings. We have higher temperatures, which can be obtained by the electron beam, and this is the reason because of we can think to add also ceramic oxides, like in this list, and obviously the cost, if in comparison, is quite sensible higher, because we do have all the part of the electron beam generation and all the part of the magnetic equipment which is necessary to guide and to focus the electron beam. But have a look, in any case, to these figures. You see here, with a basic configuration, that's the deposition rate. In the best cases, we can achieve something which is in the range of 20 angstrom per second or 100 angstrom per second, so very, very low deposition rates. And so this should request, if you should not have any deleterious effect related, for example, to residual stress and other, that if you should want to fabricate something which is 1 millimeter thick coating by using this technology, you could need also 1 year of treatment. That's it's a solution which is not industrially useful. And so thin films, thin coatings, due to the fact that the deposition rate is very low. And these are very low values. We can make something to improve these, as we will see later. But again, and with our improvement, we can achieve the level of coatings in a reasonable industrial time, which have a final thickness of some micrometers. There is also another important issues which must be considered, is that if we, let me say, want to deposit a sort of alloy, let's say alloy, well, we have different elements in our materials, and different elements, as we have also seen here, they can have different values of vapor pressures for the same temperatures. And so we could have vapor concentration of the evaporated elements, which is different from the source concentration. So we can have stoichiometry problems. That's the way for which this parameter has been considered in the general list of the important parameters for the thin film processes. And it must be seen if the final resulting composition can be considered suitable to the design purpose, because we can fabricate coatings in the case not of pure elements, but in the case of compounds, alloys, for example, having a final composition which is different from the starting materials. For both this process, as well as I would say also for the sputtering, which will be the next step, we see and we say also, this applies also to the thermal spray processing technology. I didn't mention to you, but the concept is also the same, that this kind of technologies, so the PVD evaporation technologies, is a line of sight deposition process. That means if we put here the source, we can make the coating only on the surface which can be seen by the source. This means line of sight. And we do have, for example, holes or discontinuity in geometry in which the condensation step is not allowed to happen because these are hidden areas. And so this means that the shape of our component to be coated cannot be whatever we want, but must respect the principle that we are able to put our coating on only if the area is not hidden, is a line of sight area for the source, which is then evaporated. That's a case instead by using sputtering. It's a special case with which we can fabricate a quite special types of coatings that are called, then we will see there are also commercially available solutions, superlattice coating, by special materials, nitrides, this is chromium nitrides and niobium nitrides, in the forms of multi-layer coatings. Is a sputtering system, so we do have, as we will see later, ions which are able to sputter out materials from our source, our target. There are some special cases in which we can use a vacuum chamber filled, as we said, and as we see here, by a reactive gas inlet. And for example, in this case, we can start by using nitrogen as a reactive gas inlet. We can have a source of chromium, we can have a source of niobium, we can have niobium and chromium atoms which reacts with nitrogen to form a chromium nitride and niobium nitride. And if, for example, we rotate this substrate with a selected, let me say, choice, we can have the fabrication of a first layer of chromium nitride. Then we can have the fabrication that applies also on this other surface of niobium nitride, etc., giving rise to multi-layered coatings. They are called superlattice in the case in which, and this is the case, the thickness of the single layer is something around, as we said to you, said before, around 10 or something a little bit higher nanometers. Thus reaching the final coated thickness by having a layered structure inside the coatings, in which each layer has a thickness of the order of 10 or something more, I repeat, nanometer. And this is one of the classification of the nanostructure that we have seen when we have started at the beginning of our discussion to discuss about classification of nanostructured materials. Sputtering, let me just discuss this and then we will stop. As we said, instead of using head to evaporate materials, that is to eject materials, we can bombard the surface with high-speed particles. These are high-speed particles, typically are ions. The moment transfer from these high-speed particles, which are going to impinge, to impact on the surface, are able to give enough energy to allow the surface atoms to escape. And when these atoms have been ejected from the surface, they can travel to a substrate and they can deposit in a film. So we do not have evaporation, we just have atoms which are ejected due to a mechanism of mechanism for which these high-speed particles are impacting on the surface, dissipating the energy. Electrons give energy in the forms of thermal energy. Here we do have instead energy which is given by impact to high kinetic energy of the particles, and thus what is going to happen, let's say here, for example, you see we can have this atom or ions with high kinetic energy, which transferring its energy is able to let atoms or ions from the substrate to escape from the solid state of the surface of our source, and then having these atoms which can be deposited on our substrate. And again, in this case, as this we have discussed here, if we are going to use a reactive environment, then we can have a reactive PVD processes which are based on sputtering. The most used form of sputtering is the DC magnetron sputtering, in which we use again a low chamber pressure to maintain high deposition rate, but we use magnetic field to confine electrons near the target to sustain a plasma that is ions, which are used in order to have this colliding, this Bombard effects on the surface of the materials to be used as a source for our coating. And this, in the case of sputtering, can give to us, with respect to the standard solution, the possibility to increase, you see here, that's the most important thing, increase the deposition rate even of 2 orders of magnitude, thus resulting in those final deposition rates, which represent actually the most performing PVD, in terms of industrial time requested for the fabrication of coatings on our component, the most performing PVD technologies. That's just a comparison. Resuming what we have said in terms of comparison between evaporation and sputtering, and the most important thing is related to the increase of the deposition rate. For today, I will stop here, and then we will start looking to some examples of coatings fabricated by this class of techniques on the next meeting, which will be next Monday. So for today is all. If you have some questions. Okay, I don't hear any questions, so have a good weekend and see you on next Monday. Bye-bye to all.